SATURN is developing a range of technical solutions to reduce the impact of shipping noise on marine life.
Most of these solutions focus on propeller cavitation, but the engine room is also considered. A propeller generates thrust because the pressure on one side of the blade is lower than on the other side. If the pressure becomes lower than vapor pressure, water evaporates and a cavity is formed. The propeller rotates through the ship wake field and therefore it experiences a varying inflow velocity. Therefore the loading is also varying. When the loading is increasing, a cavity is formed, and when the loading is decreasing, the cavity shrinks and it collapses. The collapse of a cavity is a very efficient noise source, and as cavitation noise rapidly increases with ship speed, it is usually the dominant noise source for merchant ships when they sail at their design speed. To reduce the impact of shipping noise on marine life, it is therefore important to reduce cavitation noise.
One solution tested was the performance of 2 air injection systems to reduce underwater radiated noise from ships.
In the SATURN project, we performed experiments to quantify the performance of 2 air injection systems for reducing ship underwater radiated noise. One system, the so-called masker system, was tested using this model. The machinery noise was simulated using a vibrating metal section, and air was injected through these hoses and flowed along the hull like this. The second system, the so-called Prairie System, was designed to inject air bubbles into the propeller disc in order to dampen the collapse of cavitation and thereby reduce its underwater radiated noise. We are now standing in MARIN's depressurized wave basin, where we perform cavitation and sound measurements of scale models of ships. We tow the models using a carriage over a set of hydrophones which measure the sound. In the SATURN project, we performed measurements with and without the air injection systems engaged in order to quantify their performance. We found that the masker system offers reductions of up to 20 decibels in terms of underwater radiated noise, while for the Prairie-like system, this was about 10 decibels.
Another solution was the development of an innovative pump jet propulsion system to reduce underwater noise caused by cavitation.
CETENA is investigating a technical mitigation measure for ship underwater radiated noise. In particular, we have developed an innovative pump jet design with the aim of reducing the cavitation related underwater noise and increase efficiency. The pump jet is a composite propulsor made of a rotor, a duct and a stator. The role of the stator is to provide part of the thrust of the pump jet and to recover part of the rotational kinetic energy lost by the rotor. The role of the decelerating duct is to decrease the speed of the water in the gap between the rotor and the duct, and so delay the inception of the cavitation there.
Here we are in the test section of the large cavitation channel of CNR, that is one of the biggest facilities of this type worldwide. For these activities, we applied advanced experimental methods to correlate radiated sound events with propeller flow characteristics. So by these methods, we have been able to quantify the potential of a pump jet propulsor for sound mitigation and efficiency improvement in comparison with the conventional propeller, and we were also able to understand the fundamental underlying mechanism of sound generation and radiation related with the dynamics of propeller contacts.
Thanks to this feature, the pump jet is expected to increase the efficiency in comparison to the original propeller and to delay the cavitation inception on the rotor.
Finally, SATURN tested alternative propulsion systems such as the trochoidal propeller.
In the SATURN project, we've been working on a trochoidal propeller, which is a vertical axis propeller, this way. In the specific kinematics is that the blades are turning on a given disc and each blade is oscillating separately. So the combination of the movement of the water due to the ship velocity plus the rotation of the disc, plus the oscillation of the blades, produces the movement of a fish tail in the water. Our contribution in the SATURN project was on two aspects. First, we did a set of experiments on a model of a ship equipped with this kind of propeller, and we tested it on a lake to measure the performances in terms of power and the underwater radiated noise in the lake. We also made direct computation of the radiated noise in terms of numerics. So we computed the radiated field of pressure to make the direct contribution of the noise plus the vibration of the blades in the flow, and we compared these results with the measurements we had from the test in the lake. This agreed very well. We already knew from previous research that this kind of propeller is very efficient in terms of propulsive power, and we anticipated that it would be also very interesting in terms of underwater radiated noise, which is the main concern of the SATURN project.
These tasks were preceded by studies to improve the understanding and prediction of propeller noise, followed by a detailed cost-benefit analysis and the production of a source-level assessment matrix. Deliverables and other publications of the SATURN project can be found on the SATURN website.